And today we're going to look at sort of vaccines and the immune response. And I wanted to start off, well actually I'll just run through the learning outcomes first. But at the end of today's lecture, you'll be able to define vaccination and also the criteria that makes an effective vaccine. We'll be able to understand the difference between passive and active immunization, also to compare the primary and secondary immune response and that context of immunological memory, and then also be able to understand some vaccine routes and being able to determine their success. Also being able to understand what an adjuvant is and how adjuvant works, and then also the description of herd immunity. I just wanted to do a quick poll everywhere quiz, so if you can just sort of have a go at that. But essentially the question is, the year is 3709, and a new disease has emerged and it's infecting hundreds of people each week, and the scientists have developed a new vaccine to help prevent the spread of disease. So what systems are scientists depending on to see efficacy? So if you just have a go at the poll everywhere, there's just one multiple choice question. But essentially, as the majority of you are choosing, it is of course the adaptive immune response. So when it comes to vaccination, what we want to do is we want to trigger the adaptive immune response in order to create a memory, so we get long-lasting protection from that particular pathogen. So obviously you just need to bear that in mind, that when it's coming to vaccination, we really want to trigger that immunological memory, and we're doing this through the adaptive immune response. So I'll switch back to the presentation. Okay, so let's have a look at vaccine development. So I'm sure you probably appreciate that since the beginning of the pandemic and in early 2020, really sort of virology and immunology really sort of took a prominent role in daily life, and there was really sort of significant public interest into how our immune systems could battle a virus. And also there was sort of great sort of expectation and anticipation about how quickly we could create a vaccine and how quickly that would become available. And we actually saw the most rapid sort of rollout of a vaccine in human history, as well as some sort of very good sort of technological developments with that. But the key thing that you need to remember is obviously the main goal of vaccination is that we want to generate long-lasting and protective immunity, as we just saw in that poll everywhere exercise. So when it comes to a disease-causing organism, when we want to generate a vaccine from that, we can either use an antigen, a small fraction of that disease-causing organism, or we can take the whole organism and attenuate it, or effectively weaken it, or use a killed version of it to generate our vaccine. But there are also other things that we need to consider. So in addition to what antigen we're going to use, we also need to consider the presence of an adjuvant, any preservatives, stabilizers, surfactants, or any other kind of components that we need to consider in that. And then of course, typically you move through several different phases of testing it out and making sure that it's safe. In terms of vaccine development, you probably remember this figure from earlier on during the module, but essentially about 25% of worldwide deaths are actually associated with communicable diseases that you can see in blue here, and they kill, or they're responsible for about 12 million deaths annually. Now obviously the presence of vaccines can really help to reduce these numbers, and also it has long-term impacts on health and productivity. And you can see that in this graph here. So here we're looking at the return on investment, and you can see that immunization really sort of gives a good return. So we're spending a lot of money on immunization, but we know that infections mainly infect young children, and therefore education really depends on having healthy children. So therefore it's a good return on our money to sort of put it into immunization to make sure that we've got healthy children. But also remember that infectious diseases are a particularly problem, not just for the young, but also the elderly and the vulnerable. So we need to factor all of that into our decision making. Now, when it comes to active versus passive immunization, so passive immunization would be when you sort of deliver a preformed antibody into an individual, and this is obviously a temporary situation because it's not engaging the host immune response, and it's quite an old-fashioned method, but several conditions still use this passive immunization. So can anybody think of any examples of passive immunization and how we might use it today? Any ideas? So immunodeficiency, so obviously we can use it there, but also you're probably more familiar with it in the use of antitoxin or antivenom, because if you have an immediate threat to life, obviously if you're able to use an antitoxin or antivenom, you can neutralize that before it damages the body. But also exposures to pathogens that would cause death or severe damage quicker than an immune response can be amounted. So if you think about neurons or polio, which actually affects neurons, you really want to avoid that situation from occurring, because obviously you can have paralysis or things like that. This is just an example of some agents that sort of we can use. So we've got horse antivenom, horse antitoxin. So this is for like spider bites, tetanus as well, varicella zoster, so hepatitis A and B. And you can see that quite a few of these use, they're actually derived from horse. This is because horses actually can mount quite an effective, strong, robust immune response. They're also quite large, but effectively, it's a good source for making these passive immunization antibodies. But when it comes to active immunization, obviously vaccines are a good example of active immunization. So here, as we mentioned in that Paul Evero quiz, we're triggering the adaptive immune response, and the aim is to trigger immunity, but also memory that will give us a long-lasting protection, so that protection is in place if we ever do encounter that infectious disease, and hopefully avoid us getting that. So when it comes to making a vaccine, how are we going to do that? Well, really, it ties in not just sort of the rational design, but also basic research, and we need to sort of work with those hand in hand. So obviously, we'll start with basic research, and this will enable us to sort of uncover and discover the immunogens or the actual antigens that we need to use in order to be recognized by B and T cells, mount a proper response against the pathogen. We also need to choose our specific immune targets, or these are often known as the correlates of immune protection. So this is really sort of defined, it's defining sort of the immune response from a vaccine or a natural infection that would trigger an immune response so that we can actually sort of be protected from the virus. And in some situations, we may want to consider whether we actually will benefit from having sort of high circulating levels of IgG, or whether perhaps we would want sort of secretory IgA in a mucosal environment, because obviously depending on what pathogens we're looking at, that will determine sort of what antibody we would like to be produced, especially if you're looking at a virus that will infect the airways, mucosal surfaces. So really what you want to do is you want to sort of identify the specific memory response that you want before you encounter that pathogen, so you can prevent. When it comes to actually the criteria of effective vaccine, these are listed here, but I just want to mention that it's really important to remember that vaccines are a public health strategy. They're not a personal health strategy. And we'll touch on that later when we talk about herd immunity, but just kind of keep that in mind. So some of the criteria, we obviously want it to be protective, so we want it to protect us against the illness that we may experience if we were to be exposed to that pathogen without it. We want to also consider whether it induces a protective T-cell response, especially if it's an intracellular pathogen such as a virus, because that will need to be dealt with by the cell-mediated processes or responses. Also, there's some practical considerations. So you want to think about the cost per dose, because you obviously want it to be affordable, the biological stability, the ease of administration, and of course whether it's got side effects. So, you know, if you're considering a vaccine that needs to be stored in a -80 freezer, then that obviously, you know, may affect its biological stability if you're trying to roll it out to rural areas or more developing countries. So you need to think about those things too. Whether it induces a neutralizing antibody. So as I mentioned, this is particularly important for diseases like polio, which obviously infect neuronal cells, which cannot be replaced. So therefore, you really want that neutralizing antibody to sort of prevent that infection taking a hold in those cells. And also sustained protection. So this is the memory response that we want, because we want it to give us a long-lasting protection. And of course, safe. We want to make sure that it's safe, that the vaccine itself is not going to cause any illness or any associated deaths. But also, and you probably appreciate this with the whole sort of COVID pandemic, is that we want it to be perceived as safe. So we really need the public to be on board in order to adopt the vaccination and make sure that we can achieve our herd immunity. So these are all things that you kind of want to consider when you're developing a vaccine. This is just some examples of vaccines that we have that are currently available for bacterial diseases and viral diseases. So you can see that we've got vaccines against tetanus, pertussis, cholera, tuberculosis, typhoid, and meningitis. And then when it comes to the viruses, obviously measles, mumps, and rubella, so that's your MMR combined vaccine, polio, chickenpox, influenza, and then of course HPV, and as we all know, SARS-CoV-2. Now, having said that, there's still sort of an unmet need to generate vaccines against many sort of important infectious diseases, which sort of currently lack an effective vaccine at the moment, and this is an example of some of the diseases here. But in certain situations, you'll be aware that obviously we can be infected with a pathogen, but we don't generate a protective immune response. And then examples of that will be HIV, so we know that hides out in your CD4 cells, tuberculosis and malaria. These all kind of avoid the immune system somewhat. So really, you know, it would be very beneficial if we could generate a vaccine against these diseases. But also, you need to bear in mind that a vaccine that can be effectively developed and used in a developed country may not be so applicable, you know, in a developing country. So that's the issues that I talked about earlier. That obviously, if you've got, you need to think about storage and deploying it. So if you need a vaccine that obviously must be kept in a -80 freezer or something like that, then that's a significant barrier to rolling it out into developing countries. And also, you need to think about, you know, who's going to deliver that vaccine, whether it's going to be a health professional that requires an injection, or whether it's something that can be just put on, you know, like an oral or an inhaled vaccine. They're all things that need to be considered. And then I just wanted to sort of bring you back to just sort of a little bit of revision in terms of immunological memory, because obviously, as I've kept saying today, the most important consequence of an adaptive immune response is really being able to establish memory and give us that long-lasting protection. So when we encounter a virus or antigen, this is presented on your dendritic cell to the T cells. Also, it's recognized by B cells, which will get T helper cell help. We also have our memory and our effector cells, so our memory cells obviously give us that long-lasting protection. You also need to remember sort of affinity maturation through somatic hypermutation, as well as the antibody class switching. So this is where we're generating, you know, the different classes of antibodies, but we're also kind of refining the antibody affinity. But ultimately, you'll be left with your memory T cells, your memory B cells, but also sort of initially your plasma cells that will secrete the antibody required. So really, this sort of represents, you know, the kind of ability of our body to respond more rapidly and more effectively to pathogens that we have already sort of encountered. And if you look on this graph here, so we're looking here at the primary adaptive immune response. So we have an exposure here, so you can see that it takes a little while before the immune system or adaptive immune system is kicking in, and then we're getting sort of a rapid incline of our antibody and effector T cells. And then these will gradually start to wane off, because obviously we don't need them anymore, so we need to sort of clear them away, because it's not good to have an elevated immune response all the time. So what happens sort of when we have a second exposure or a second challenge? And that's what we can see here. So after our first exposure, we still sort of have like high levels of antibody. These are obviously good at neutralizing if we sort of encounter that infection again. So that's why I've called it sort of repeated aborted exposures, because you get infected, but you've actually got neutralizing antibody, so it never takes hold. But then here we get a second exposure. And hopefully what you can see is that the second exposure really is qualitatively different, because you'll see that it's more immediate, so it happens much more quickly, and it happens much more strongly. So you can, in comparison to the primary response, you'll see that it's much stronger and much quicker. It's important to remember that in this instance of a secondary exposure, that it's the pathogen-specific T and B cells that are really sort of outnumbering the naive cells in this instance. And also that the memory cells are more readily activated than the naive cells. So if you think back to when we were talking about the original antigenic sin in the first few weeks of term, and also because memory cells will be recirculating through the tissues, not just the lymph nodes, so they're kind of there and they can encounter the secondary sort of infection quickly. But generally overall, just be aware that we're getting this preferential activation of the memory response in preference to the naive cells. So if we look at the antibody level and antibody affinity following different exposures, so you can see that after the primary exposure, sort of we have a peak of IgM, and then after sort of repeated exposures, you'll see that this is sort of overtaken by IgG, so we're getting our class switching going on here. And also if we look at the affinity, we'll see that the affinity increases, and it increases as we get more exposures. So in the primary immune response, we're getting this isotype switching, we're getting some somatic hypermutation and affinity maturation, so we're getting our different classes of antibodies being made, but we're also sort of increasing that affinity, so we're tailoring and tweaking that antibody. So when it comes to a secondary response, we've actually got antibodies that are inherently better, and we can sort of get further refinement of them. But it's important to remember that the antibodies that we get during a secondary and any subsequent exposure will actually be quite different to the antibodies that we see in our primary response. And as I mentioned before, any subsequent responses will tend to get quicker because we've kind of got that immunological in place. Now, in the past, we've always kind of talked about memory T cells as being one, but actually they're sort of two subsets that we need to be aware of. So we've got the central memory T cells and the effector memory T cells. Now, the central memory T cells, these circulate in the lymphoid organs, and that's why they're positive for L-selectin and CCR7, so they can move in and out of the lymph nodes. And then we have the effector memory cells, so these are negative for L-selectin and CCR7, and they actually circulate in the non-lymphoid tissues. It's important to remember that individual memory cells, they do actually have a limited lifespan, and whilst quite a few of them are quiescent, what will happen is some of them will proliferate, and this actually sort of replenishes and keeps going that population of memory cells. But it's also important to remember that the effector cells will die after a few days through apoptosis, and so therefore it's dependent on the central memory cells and effector memory cells for keeping our immunological memory going. Because obviously, as we mentioned before, you don't want your actual effector cells to be kicking around for a long time after you've sort of had infection. And that's kind of shown here, that generally you do kind of get a slight decline of your memory T cells, but really this is what keeps the memory going after we've actually cleared away our effector cells. So we're keeping that immunological memory, but we're kind of overall kind of reducing that T cell level down. So that's what you want to find. But also, the take-home message is really, it's not the persistence of antigen that's actually required for memory. And then I've just put this up as kind of revision purposes, so I won't run through it, but it's just kind of detailing the differences between a primary response and a secondary response. So I'll just leave that for you guys to go through in your own time. And then this is just having another look at immunological memory, but this time with a little bit of focus on influenza. But quite often, a lot of people might joke that, why haven't we created a vaccine against the common cold yet? Because we know that generating a vaccine that really sort of generates a long-lasting protection against coronaviruses, influenza or RSV is actually really difficult to develop. And there's several reasons for that, and I'm sure you can remember some of them. But one or two of them, because the disease has very short incubation periods. We also have a sort of like rapid host-to-host transmission. But also, hopefully you'll remember, is that the viruses themselves are highly mutatable. So, influenza and the coronaviruses, they've all got RNA, they're all RNA-based. So therefore, when they replicate, they tend to be error-prone, and they can introduce mutations, and these mutations can obviously lead to changes in the epitopes, and basically it kind of plays a key role in being able to escape the protective immunity that our bodies generate. And this was a figure that was shown earlier on in the module, and it's just looking at sort of the first infection onwards through to about the fifth infection. So you'll see that on the first infection, we mount a primary immune response against epitopes A, B, C, and D on influenza. As the virus starts to mutate and we get different versions of the virus coming about, what you'll see is that we have different epitopes, but essentially we will primarily use memory response to target these. So the second infection, we will still recognize epitopes A, B, and C, and then we get the third infection, and the fourth infection, which is only recognizing A, which we had in common first infection. But by the fifth infection, all the epitopes have changed, and we need to mount a primary response. And hopefully you'll remember this is the original antigenic sin, where we preferentially will sort of trigger a memory response as opposed to a primary response. So if we've got that memory, it will be used, even though we'll not be recognizing the full set of epitopes actually present on that virus. If we go back now and look at actually sort of the origins of vaccination, so this is kind of really stems from Edward Jenner and the actual eradication of smallpox, and really, vaccination has kind of grown out of this. And probably one of the greatest sort of immunological triumphs was actually the global eradication of smallpox in 1980. It's important to recognize that immunization in one form or another has been around for quite a long time. So even as back as the 1400s in China, people were practicing variolation. So this is where you would take a small amount of dried material from a smallpox scab, and then you'd actually use it to infect or create a mild infection, hopefully, in an uninfected individual, and this would be followed by long-lasting protection. But as you can imagine, this is a bit of a game of Russian roulette, and it could be fatal, and it's not really not controlled at all. But really, Edward Jenner's sort of main achievement was not only realizing that an infection with cowpox would actually provide a long-lasting immunity against smallpox without any sort of significant risk of disease, but also sort of its experimental proof, because he then subsequently variolated people whom he had previously vaccinated. And we'll talk about that in a little bit more detail. But obviously, what you want to remember is that an individual, or cowpox, is basically milder, or a milder infection than smallpox. So smallpox is very severe, but cowpox is much milder. But essentially, Edward Jenner came up with the process of vaccination, and it's called vaccination because it's named after the Latin word for cow, which is vacca, so that's where vaccination, the actual name, comes from. But what Edward Jenner did is he took sort of pustule from a milkmaid that was infected with cowpox, and he inoculated this young boy, James Phipps, with the cowpox pus. And he became ill, obviously with a small or mild disease of cowpox, but he then took scabs from an individual that actually had smallpox and then inoculated this boy again with that. But in this instance, he actually avoided getting smallpox because he had protection against it. So obviously, you're not going to get away with kind of doing an experiment like that today, as you can imagine. But that was essentially, the first vaccination kind of model, or the proof that we could actually sort of get a long-lasting immunity by kind of infecting an individual with a milder strain, which was cowpox. So we look at sort of cowpox and smallpox. So you can see that they share sort of similar surface antigens. So if an individual is immunized with cowpox, they will generate an antibody response sort of against the surface antigens of cowpox, and these will actually be able or capable of neutralizing any subsequent exposure to smallpox. So that's essentially how it's working. Now, the reason that we were able to sort of develop such a long-lasting immunity against smallpox, but also we were able to sort of globally eradicate smallpox, was because smallpox really evolves very, very slowly, and it has conserved antigens. And what you need to remember is it's a double-stranded DNA genome, so it's much more robust, much more stable. It has more sort of proofreading capabilities, and it's less likely to make mistakes. So therefore, once we've generated an immunity against that, it's a long-lasting immunity, and it's not going to change because the virus itself is not going to change. We also had good success with it because there's no animal reservoirs. So once we broke the chain of human transmission, that was it. The virus can't survive. Obviously, if there's an animal reservoir, then that's another obstacle that we would need to consider. But it was actually another doctor, John Fuster, who actually had realized that the prior infection with cowpox, which as we mentioned is milder and less virulent, actually sort of confers immunity to smallpox. So he was the one that had made that kind of initial observation, and then it was actually Edward Jenner that then came along and realized kind of the significant implications of this, and then did that experiment with James Phipps, proved that it actually could work and actually proved the concept of vaccination. So that's really kind of the origins of it. We also need to consider the location, because where you want to actually sort of induce the vaccine into the body is a key thing to bear in mind as well. So just if you think about it, most of the vaccines that you've probably had tends to be sort of subcutaneously or intramuscular, so an injection. And as we know, they're all sort of rather painful, and people don't like them. And so there's a worry there that that might reduce uptake. And of course, when we were talking about rolling it out to developing countries, you need sort of more specialized equipment, obviously individuals that can deliver the vaccine, so you want trained nurses and doctors, and you require all the needles, syringes to go with it. So they're things that could be a barrier. But then also you want to consider, where is it that most pathogens will actually infect an individual? And of course this will be like your mucosal sites. So therefore you kind of want a vaccine that would stimulate immunity locally where you might experience that disease or that infection. So this is obviously just showing you some sort of examples of vaccination routes. But it's really, what's the most appropriate route to achieve the immunization? Is it going to be intramuscularly with an injection, or is it actually going to be through the mucosal surface as an oral vaccine or as an inhaled vaccine? So then if we look at what challenges we have to sort of immunize individuals, that should be mucosal surfaces. But again, just sort of kind of bringing up this kind of bigger picture. Because really what we want to do is we want to trigger that immune response at the main site that we sort of actually encounter that infection. But bear in mind, obviously, that the mucosal surfaces, they account for a very large surface area. We've got the GI tract, respiratory tract, and also remember, especially in the GI tract, they play a really crucial role in homeostasis, as well as sort of interactions with the microbiome. But also, particular dietary antigens that you may be encountering in the environment. And we'll kind of touch on that in a little, well, actually we'll touch on it now. But developing essentially new, safe and effective mucosal vaccines is challenging. So can you think of why that might be, bearing on what we just said? Obviously, your mucosal environment, it's got a lot of interactions with the microbiome. You've got a lot of other interactions going on. So what else is occurring, sort of, especially in your, let's say, your GI tract, for example? You're encountering a lot of heavy sort of antigenic load through those mucosal surfaces, especially in your GI tract. Could potentially be a challenge to a vaccination as well. But basically, I want you to think about tolerance, because obviously, when it comes to your GI tract, as I mentioned here, you're getting this really sort of high antigenic load, and you're getting this exposure to microbiomes, and so it's really important to sort of maintain homeostasis, because we don't want to get these sort of chronic inflammatory responses. And this is, thinking back to tolerance as well, and how that might play a role if we were to have a mucosal vaccine as well. So they're things that you just need to consider. This is just a slide that's giving you some examples of mucosal vaccines. So basically, these are diseases which have an unmet vaccine need. Pneumonia, some sort of influenza, or this Haemophilus influenza, RSV, then of course HIV and Hep C. And then we've got our licensed mucosal vaccines, so these are ones that are sort of currently in use. So we've got ones against cholera, influenza A and B, salmonella, poliovirus, so these are all the vaccines that you may well have had like on a sugar cube, and then rotavirus as well. And of course, for influenza A and B, they do have a nasal spray, but they tend to give this to younger children. And then I also just want to sort of bring you back to the link between the innate immune system and the adaptive immune system. Because, just to refresh your memory, that obviously when you get an infection, it's initially recognized by the innate immune response, and this is what elicits that sort of immediate defense. We have the detection of the pathogen-associated molecular patterns by PRRs, and this will not only induce sort of the inflammatory response and innate host defenses, but also it's really kind of crucial sort of, in terms of activating the PRRs on the antigen-presenting cells, so on your dendritic cells, for example, and that this will ultimately lead to our sort of generation or activation of our adaptive immune response. So we need to remember that link between the innate and the adaptive immune response. And it's really worth stressing that it's not just enough to sort of include our foreign antigen of interest in a vaccine. And this is where we really need to come on to adjuvants. And actually, what's his name? Charlie Janeway. So Charlie Janeway, who actually wrote the immunobiology textbook, so he was quite a leading immunologist. And he used to call this the immunologist's dirty little secret, that essentially, if you introduce a foreign antigen, that may not be enough to introduce an immune response, that you really needed to include something like LPS, or essentially what we now would call an adjuvant, in order to trigger an effective immune response. And so really, the take-home message from this slide is that if you want a successful vaccination strategy, you need to consider the innate immune system as well, okay? And obviously the desirable response from a vaccination is that we want to have high antibody levels, we want to have a strong T-cell response, we also want to have quite a wide breadth of epitopes that we can recognize, and obviously a prolonged protection at that particular site that we would encounter pathogen. So we have a little bit of a look in more detail at adjuvants. So adjuvants are really important if we have a vaccine that is based on peptides or purified proteins, because we need to mimic sort of that real life infection and get that activation of the adaptive immune response. But essentially what an adjuvant is doing is that it's enhancing the immunogenicity of your antigen that you want to use. vaccine. Now, the adjuvants will work because they trigger sort of the viral and the bacterial sensor pathways. So these are your toll-like receptors and your nod-like receptors that you'll be getting sort of on your dendritic cells. And these are some examples of adjuvants. So we've got the lipopolysaccharide, which is a TLR4 agonist. We've got alum, so this is aluminium hydroxide or aluminium phosphate. This has actually been used since the 1920s. This is actually activating NALP3, so if you remember back to NALP3 and the inflammasome. And then we have MF59, which is actually sort of an oil in water emulsion. But really, you know, we've had a bit of a revolution in our understanding of the activation of the innate immune system through the PRRs, I can't speak today. And this has also sort of led into basically improving our understanding of how adjuvants work, and basically, you know, the use of adjuvants in triggering the innate immune response, but basically sort of ultimately activating that adaptive immune response. It's really important to realize that. This is just an example of some adjuvants. As we mentioned before, the mechanism of action for an adjuvant is we want it to provide those damage-associated molecular patterns, or the PAMPs as well. We also want to sort of be able to deliver it to the antigen-presenting cell, but also activate PRRs. This is just showing you an example of some sort of commonly used adjuvants that we've sort of had over the decades, and then also some examples of adjuvants that are available in various across. When it comes to vaccine safety, you know, that's another thing that we need to bear in mind. So obviously we want to have you know, a strong protective immune response, and we need that adjuvant to do that. But in some vaccines which use like a weakened or killed pathogens, because they're sort of the whole cell pathogen, they actually have naturally occurring adjuvants, and that can be obviously beneficial in those. But as I mentioned before, any vaccine that just has a peptide or a small fragment of the pathogen will require an adjuvant in order to trigger the immune system. But adjuvants themselves can cause problems, so we can get sort of localized reactions, sort of redness and swelling and pain at the injection site, or possibly a more systemic reaction such as a fever. But of course we need to monitor them, but essentially it's a bit of a balance here. You know, we have the benefits of reducing the incidence of disease, but then we have, you know, also on the other side, what risks we may get sort of adverse reactions to. We can look at that with sort of a focus on a couple of different sort of diseases. So this is looking at measles and diphtheria. So you can see here we've got the cases, the number of cases, and we can see that as the vaccine rate or the coverage increases, we get a reduction in the disease, and that's true for both measles and diphtheria. It's really important to remember that a vaccine isn't risk-free and that everyone will react differently. And again, it's just a bit of a balance here, and these are just some figures for you. So you can see that in terms of measles, the risk of getting pneumonia is 1 in 20, encephalitis 1 in 2,000, 1 in 3,000 for deaths. But if we look at the risks of the vaccine, it's 1 in 100,000 for getting a severe allergic reaction, or 1 in a million for getting encephalitis from the vaccine. And then if you look at pertussis, risks of pneumonia 1 in 8, encephalitis 1 in 20, death 1 in 200. But if we look at the risks from the vaccine, we can see that for encephalitis it's 1 in a million, or no risk from death. So basically, hopefully you can see you know, the benefits are quite clear, but we still need to consider them. And then I just want to touch on this. So has anyone heard of Andrew Wakefield and the MMR vaccine? No? So I've entitled this slide sort of "Vaccines may be a victim of their own success." But essentially, Andrew Wakefield was a doctor, and he published basically a case study in 1998, and this suggested that the MMR vaccine, so this is mumps, measles, and rubella, that there was a link to autism in children who got the vaccine. Now, it's really important to remember he only did this in a sample size of 12 individuals, which is obviously a big flaw. There was no controls in the design, and he also made very speculative conclusions. But unfortunately, the paper, as you can imagine, received widespread publicity, and this caused parents to panic and pull their children from getting the MMR vaccination, and MMR vaccination rates dropped. Now, immediately afterwards, they did do several independent sort of epidemiological studies, and these kind of completely refuted the link between MMR vaccination and autism, and ultimately the paper was retracted, and the authors were actually found guilty of deliberate fraud, falsifying facts for financial gain. But of course the damage had been done. So again, obviously some of the problems with this was the n=12 sample size. No other group could confirm his findings. There were also financial conflicts of interest and falsified data. But as you can see here, we're looking at the vaccine coverage, and you can see about 1998, vaccine coverage starts to drop. And then, of course, as it drops and we drop below the herd immunity, we get a sharp uptake in actually the number of confirmed measles. So you can see that obviously that caused a lot of problems and a lot of doubts in vaccination that probably still linger to this day. And then that kind of links on to herd immunity. So this is essentially where we get the indirect protection from infection. And as I mentioned earlier, a vaccine, it will protect the individual, but it also has population level effects. So it's really important to consider that a vaccination is not just for you, it's for maintaining that herd immunity within the population. Because when a high percentage of the population is vaccinated, it's really difficult for an infectious disease to spread because there's not that many people that it can spread into. And that's shown in that diagram here. So here we have no herd immunity, we have an infected individual, and it's just going to run wildfire through the population. However, if we have herd immunity, so we've got a large number of immune individuals, we'll see that basically that's a barrier to that disease spreading in the population. Now, it's really important for protecting vulnerable individuals, but also, we used to think that a vaccine would offer us protection as an individual for life, but we know that that's not true. But really, it's herd immunity that's protecting sort of us as like a herd, essentially. And an example of that would be that if we have sort of low vaccine coverage and you have a child that's not vaccinated, when you send that child to school, it's likely that they're going to be coming in contact with children that are not vaccinated either, and therefore that vaccination can be passed on relatively quickly and unimpeded throughout the population. Again, it's really important to remember that vulnerable people depend on herd immunity. So these are people with a weakened or deficient immune system, elderly individuals, as well as newborn babies, because you remember when you're a newborn, it takes a little bit of a while for your immune system to kick in once your maternal antibodies have waned. But of course, there are some critics of herd immunity, and they may state that we need a better understanding of the dynamics of the herd immunity, how long this protection is going to last, but also the impact on the microbial biology. So if you think about herd immunity, what sort of selection pressures that might put on the virus to evolve and to try and overcome that herd immunity. But also, as we talked about before, what are the side effects of a vaccine on the immune system? And this is just showing you sort of the percentages that are required for herd immunity for different diseases. So you can see that they're quite high for things like measles at 95%, and then a little bit lower for influenza and things like that. But in terms of challenges and the future considerations, we really need effective vaccines against several major infectious diseases that we still have, so there's an unmet need there. In terms of drug resistance, vaccines are a really important tool for combating antimicrobial disease. And then think about the current global spread or the ease of spread of emerging pathogens as we saw with COVID-19. And obviously, with the increased availability of worldwide travel, a pathogen can be halfway around the world in less than a day. Also, we have an aging population. We need to think about things like public perception, and that kind of links over to what we were saying before. We really need the public to be on board if we're going to achieve a successful vaccination. But also remember that vaccines are not only for infectious disease. We can use them for oral allergy or indeed cancer vaccines, and that's just a quick example there. So there is actually a quiz if you want to just have a go at this one. So let me just activate it. Right, so that should be active now. So if you just want to have a quick go at that. I'm aware we're kind of a little bit pushed for time, so we'll just go through them together. But why are antibody listing vaccines against viral disease is protective? So it looks like 100% on this one. So it's obviously so vaccine-elicited antibodies are present prior to exposure to the virus, and this obviously prevents any subsequent infection from occurring. The HPV vaccine is a mixture of the major capsid proteins from several HPV plus an adjuvant. What was the essential criteria to assess its efficacy when the vaccine was under development? So it's this first one. So basically determining whether the vaccine elicited neutralizing antibodies that can prevent HPV infection. Then how does the phenomenon of herd immunity contribute to overall protection against infection? It actually means that vaccine compliance does not need to be 100%, so that's what we were talking about earlier, that if you've got that herd immunity, you can protect the herd as long as you've kind of got to that specific level that's effective for that given disease. And then why are very young children exposed to a new strain of influenza at risk? Well, it's because they lack the useful T-cell responses that adults have because they've been exposed to previous strains of influenza virus. And then 2 cohorts of individuals are vaccinated against polio, one with an oral vaccine and the other with an intramuscular vaccine. And then comparing, what would investigation show, comparing the immune responses of these 2 groups. Well, it would be a more robust IgG response and a weak IgA response in the intramuscular vaccine compared to the oral vaccine. So just think about where you're kind of introducing. All right, I forgot the attendance pin as well. So if you guys just want to email me, so if you email me in the next half an hour, I'll deal with it. But then after that, we'll just say that close it. But apologies for that. And that's really it. So I'll just leave you with that recommended reading. And I'll see you guys tomorrow morning.